Hello and welcome to Unit 2, Lesson 4 on projectiles. This is going to be only 1D projectiles, so again, we're not going to have to worry about X's and Y's for a little bit. And it's going to be as if they're going straight up, straight down, or moving along a track, something in those regards. So question 1 is actually the throwing a ball straight up at 47 meters per second. Then we want to determine the time it takes for it to return to the same height. So if we sketch in some sort of object, which we can call a ball, and we draw this thing moving straight upwards, we know from past experience that there's going to be a max displacement on this thing, and as it reaches the top, its velocity is going to be 0, but essentially it goes to the top and then it falls from that same height. And it's going to fall back down from there. And actually what it's going to do is, because it's same object falling for the same distance as it was slowing down, its acceleration the whole time has been, well, if up is a positive direction, downs are negative. So negative 9.81 meters per second squared. This velocity down here is going to be, they're going to be equal velocities. And I'll sketch those in with little names here. We can say that this is the, that's a little bit crooked. This is the initial VI, and it tells us that is 47.0 meters per second. But really, this VF value here, the final velocity, where we're stopping this thing, is also going to be 47, but it's coming down. So this is going to be a negative 47.0 meters per second. And if you got a little lost in there, hopefully it's cleared up by the end of the question. But essentially, again, what I'm trying to say is we toss this ball up and it slows down, momentarily comes to a rest before it starts to fall again. Right? And then it has the same sort of distance that it's covering, same acceleration on it. So by the time it reaches a displacement height of 0, it's going to be moving the same speed as it was originally again. Now, real world, there's going to be probably a little air resistance, so it's going to be a little bit off. But in this physics world with perfect environments, we're going to say that it's going to be the same. Okay, the acceleration we were rolling with here, right, was negative 9.81. Actually, you know what? I want to table these up. Okay, so we had VI was 47.0. We have VF now, which is negative 47.0. Okay, now acceleration was negative 9.81 meters per second squared. Again, the negatives on these two values are because our initial velocity is up. And so we're saying in this case, our initial up velocity is positive. So if we had an arrow like this, we would say up in this case is positive. Anything moving down is going to be negative. Okay. So we have 3 key pieces of information already. We could solve for either of the other 2. And this question is asking us to solve the time. So we'll plug in time here and we'll say we want that. And the last thing missing is the displacement. Well, let's say we don't need that because we have our 3. All right. Now we have to choose a formula. We're looking for a formula that discludes displacement. If you look on the kinematic sheet, there is only one, and that one is acceleration is equal to VF minus VI over t. If we rearrange this thing to solve for t, this one's easy because really we'll multiply this up and divide that back down. So it's going to be t is equal to VF minus VI over acceleration. This is in a useful form. We just plug in values and we'll be done. So we can say that time is equal to VF, which was negative 47 meters per second, minus 47 meters per second, all divided by negative 9.81 meters per second squared. This gives us a final time of 9.58 seconds to throw this thing up quite quickly, for it to slow down and then fall back down to where it came from. All right, that's all.